Okay, so our next speaker is Hendrik Bentmann from the University of Würzburg, and he's gonna talk about imaging topological states in photoelectron spectroscopy from magnetic topological insulators to Weyl semimetals. So, Hendrik, please.
Yeah, thank you very much for the introduction, and also to the organizers for the kind invitation. So in this talk, I will present recent photo mission results on two types of topological materials. And in particular, I will look at magnetic topological insulators in this manganese bismuth telluride based class of magnetic van der Waals materials, which has already been very nicely been introduced by Anna in her talk in the same session. And then later, I will present recent results that we obtained for the Weyl semimetal tantalum arsenide, where we will basically be interested in the question to what extent we can actually address really the non-trivial topological properties of the electronic states in these materials via momentum resolved spectroscopy. Okay, before starting, let me first acknowledge my collaborators. So this is work done in Würzburg in the group of Friedel Reinhardt, and much of the work has been carried out by very skilled PhD students. So the work on the Weyl semimetals was mainly carried here by Max Unzelmann and Tim Friggemeier, and work on the magnetic topological insulators was carried out by Rafael Vidal and Philipp Kagerer, and also there were very important contributions by Celso Fonari, who's a postdoc in our group. And then furthermore, I'd like to highlight in particular a very nice and long-standing collaboration with Anna Isaeva, who's now in Amsterdam. And also in the context of this talk in particular, we had very nice laser ARPES collaborations with groups in Hiroshima and also in Jülich. Okay, just as a brief introduction, so when we start with the conventional topological insulator, it was realized early on that introducing magnetism, despite breaking time reversal symmetry, is not really detrimental for the topological properties, but rather the introduction of magnetic order introduces new types of topological states. And one type is seen here, where due to magnetic order, a gap in the topological surface state is induced, but new types of one-dimensional topologically protected edge states are generated, which in real space form these chiral one-dimensional channels, which can be used for dissipationless charge currents. So compared to conventional topological insulators, the number of materials that really actually combine this interplay between topological band structure on the one hand and magnetic order on the other hand is still rather low. So there are not many materials that realize this interplay. So one important task in the field at the moment is to search and to establish and to control new types of materials where really this interplay can be robustly observed. Now, one other important property of topological insulators is that they cannot be tuned, or their band structure cannot be tuned by some external parameter into the one of a normal insulator without going through a metallic phase. This is one of the defining features of a topological insulator. And it was realized that actually these metallic phases that lie at the phase boundary between the normal and the topological insulator can also display interesting topological properties. And one example is this well-known Weyl semimetal, which appears at, or actually over an extended region at this phase boundary once the inversion symmetry of the system is broken. So the breaking of inversion symmetry is important in this case because it allows spin-orbit coupling to split the electronic bands already in the bulk. So we get spin polarized bands in the bulk, and then this metallic state here features band crossings between spin polarized bands, which generically constitute monopoles of Berry curvature. So at these metallic band crossings, we have monopoles of Berry curvature in momentum space, and these monopoles can be associated with the topological invariant, basically the integral, surface integral over the over a sphere surrounding these Weyl points, and this topological invariant protects these band crossings. And similarly, as in topological insulators, the bulk boundary correspondence implies surface states which are generated from this non-trivial topology in the bulk, and these, according to theory, take the form of Fermi-arcs, so non-closed Fermi surface contours which connect the projections of the bulk Weyl points. And the question that I will address in particular, to what extent can we really image this non-trivial topology of the electronic states, really the Bloch wave functions in momentum space using spectroscopy. Okay, the method that we are using is angle-resolved photoelectron spectroscopy. I will just give a brief introduction here. So we use light to excite photoelectrons, which are then analyzed as a function of energy and also emission angle. And via energy and momentum conservation laws, we can deduce back from the photoemission intensity distribution on the band structure in the solid, basically. So we can even go one step further, because all the topological properties that we have seen are not only associated with the dispersion of the electronic states that we can address with ARPES, but also intimately related to the actual Bloch wave functions. And these Bloch wave functions, in fact, also enter the photoemission intensity distribution, namely as the initial state of this photoemission matrix element, which furthermore also contains the exciting light, the electric field of the exciting light, and the final state of the outgoing photoelectron. So the idea is now to use these so-called matrix element effects, so to really study the intensity distributions, for example, as a function of the polarization of the exciting light. So this would be so-called circular and linear dichroic signals, or really detecting the photoemission intensity as a function of spin, so really resolving the spin to detect the photoelectron spin polarization, and to relate these momentum distributions to the, as far as possible, to the intrinsic spin-dependent properties of the electronic structure, and eventually study the topological properties of these states. Okay, let's start with the first part on the magnetic topological insulators. So this topic was already very nicely introduced by Anna, so I will not spend too much time with the introduction. We have this layered Van der Waals compound, which resembles this well-known topological insulator bismuth telluride, but now we have introduced additionally these manganese atoms in the center of the sep-tupel layers, and it turns out that these for the 1,2,4 compound, these magnetic moments order antiferromagnetically and layer-wise ferromagnetically, and the DFT calculation for this situation shows this gapped topological surface state. So this 1,2,4 compound has been studied quite extensively by ARPES already. What I will focus on in this talk are a bit more recent experiments that we performed on this 1,4,7 compound, which was also already introduced by Anna, where this magnetic sep-tupel layers are kind of sandwiched by non-magnetic bismuth telluride layers. So this is an overview of the results. First of all, here on the bottom right, we see results on the magnetic properties, where, as Anna has already mentioned, one now sees interesting deviations from the strong antiferromagnetic state observed in 1,2,4. One observes increasingly ferromagnetic-like properties. And in the ARPES, we have now to take care of the fact that in this compound, we can have different surface terminations. So we can either have a surface that is terminated by a magnetic sep-tupel layer, or a surface that is terminated by a non-magnetic quintupel layer. So depending on which of these Van der Waals gaps defines the surface. And it turns out that on both types of surfaces, we observe topological surface state, but the electronic structure looks considerably different. So this is the result from MBT termination, where we can identify this topological surface state here, forming a Dirac-like dispersion. And this is the result for bismuth telluride termination, where it looks a little bit more complicated. And in particular, we see here at certain energies a reduction of spectral weight, giving rise to something like a gap-like feature in the intensity distribution. So now I will look a little bit more in detail at the properties of these states and try to really confirm as far as possible that these are indeed topological states. So starting with the 1 to 4 terminated surface first, what we looked at is the circular dichroism signal. So this is shown here. So basically we measure photoemission intensity distributions for left and right circularly polarized light. And this red-blue color code is the difference between the two intensities. And what we observe here is that at this point that we previously identified at the Dirac point, we in fact see a reversal of the sign of the dichroism when comparing energies above and below the Dirac point. And this is actually a first sign that this is in fact a helical Dirac state. When we model the wave function of the state roughly in terms of p orbitals, then what one expects is that we have pz orbitals and py orbitals in the upper and the lower part of the Dirac cone, but they are coupled via different phases. So there's a phase difference of pi between these orbitals. And this phase difference can be picked up by the circular dichroism due to the fact that our light electric field here in the z direction couples predominantly to the pz orbitals, and the light electric field along the y direction couples predominantly to these y orbitals. And due to this selectivity, we basically pick up the sign change between the py orbitals as pz and py orbitals as a sign change in our circular dichroism. Then we can go a step further. We also managed to do spin-resolved ARPES experiments on these states. And indeed, we observe a spin polarization. So this is a cut in the momentum plane, roughly cutting this upper part of the Dirac state. And we observe this helical spin polarization that is also expected for these states. So this is yeah, more or less the best spectroscopic evidence that we can obtain that these are indeed topological surface states. Now moving to the 1 to 4 to the bismuth telluride terminated surfaces, we in particular wanted to understand the nature of this suppression of spectral weight here in the region of the Dirac point. And what we found is that the intensity distributions for these states here depend strongly on photon energy, and in particular at certain photon energies, for example here at 6 eV and 61 eV, we highlight certain parts of the band structure with high intensity, but going to other photon energies, such as here at roughly 80 eV, these previously intense regions are suppressed and other regions are suddenly higher in intensity. And this is related to a different orbital character of certain parts in the band structure, and the fact that regions with different orbital characters are excited predominantly at certain photon energies. So it's a quite subtle effect, but basically what it allows us to do now is to identify certain parts of the band structure as derived from the topological surface state. So this is seen here. This is a theoretical calculation of the surface spectral density projected on specific orbitals here. And we see that in this calculation, basically we see the same features as here in this ARPES data. And then other projections on here tellurium orbitals, they show now features that we observe here at this other photon energy. So we get a kind of one-to-one correspondence between the photon energy dependence here of different parts of the band structure and the orbital distribution here. And this allows us now to get a hint that indeed this upper part here and this lower part below this suppression of spectral weight both belong to the topological surface state, and that this reduced spectral weight, which is also seen here in the calculation, actually arises from hybridization with bulk states, which become suppressed due to the surface sensitivity in our experiments. So this also implies that the Dirac point here for this bismuth telluride termination is buried in the valence band continuum, unlike for the 1 to 4 terminated surface, where we have this Dirac point rather nicely in the gap. So this interpretation is further supported by spin-resolved calculations and also experiments. Here we look first on the calculation. What we see is that indeed this upper part here is strongly spin polarized, but also this lower part that is in the valence band continuum shows strong spin polarization, confirming the identification as the topological surface state. And we could also confirm this experimentally by observing spin polarization above and also below this region of suppressed spectral weight. So we come up with this model here where we have our topological surface state that strongly hybridizes with valence band bulk states, and this leads to spin polarized states above and below a region with reduced surface spectral weight. So this also implies that these bismuth telluride terminated surfaces are probably not useful for any transport experiments, because any potential gaps in the topological surface state would be buried in the bulk continuum and not accessible by transport, while for the 1 to 4 terminated surfaces looks more promising. Okay, we also studied higher N compounds, so additional quintuple layers inserted into the matrix, and basically the results look very similar. So these are now spectra for 1 to 4 terminated surfaces, one for the one we've already seen, 1 for 7, and this one is for 1, 6, 10. So we have a sequence of MBT, BT, BT, counting from the surface, and the ARPES results look very similar. And here we have 3 different BT quintuple layered surfaces. One would be this one is 1, 6, 10, where we have first BT, then MBT, and then again BT. And one trend that one observes is that this hybridization-induced gap tends to become decreased for an increasing amount of bismuth telluride layers near the surface. And this is in line with the fact that when going towards bismuth telluride, this gap should actually vanish because it has not been observed for the pure bismuth telluride. One thing that we can also learn from this data is that the surface electronic structure is mainly determined really by the first van der Waals layer, meaning that the topological surface states are probably mostly localized in just one layer, and they're just really subtle changes due to the second and the third van der Waals layer. Okay. One interesting direction now in the field is to go towards the two-dimensional regime. Anna has already shown these results indicating that quantum anomalous Hall effect is possible to achieve in these types of materials. And one direction that we are following now in our lab is to realize the MBE growth of 1 to 4 and related compounds. This is just work in progress. We have already achieved to grow thicker 1 to 4 layers by co-deposition of bismuth telluride, manganese telluride, and tellurium on barium fluoride substrates, and started to characterize these samples. So in the TEM images, you can see the formation of this characteristic septuple layers and magnetic characterization with XMLD, shows antiferromagnetic order in these 1 to 4 films with a Néel temperature that seems to be in line with the one of the bulk compound. So we are now working to further optimize these films and to potentially also go into the direction of heterostructures or quantum size effects and so on. Okay, with this, I'm coming to the second part of my talk where I will present results on tantalum arsenide. So just a brief reminder on this compound. So this is in DFT at least, and the ARPES data is in very good agreement with that, semi-metal. One can see that over large parts of the momentum space, this band structure is actually gapped, but there are some regions where these valence and conduction bands come very close to each other. And looking in more detail at these regions, one indeed sees in the calculations the formation of these Weyl points. So one thing that is important is that this compound is non-centrosymmetric. So one can see already in the calculations that all these bands are slightly split, which is due to spin-orbit coupling forming now spin-polarized bands. So what has not been shown yet in experiment is that indeed these bands are actually spin-polarized. And I will show data in the following confirming this. One other question is about the Fermi-arc. So these are calculations of the surface electronic structure, and these are the projections of the bulk Weyl points. And indeed, one can see in these calculations surface states that connect to these projected Weyl points, but it's still not so clear whether these are really Fermi-arcs. So one can see that actually we interpret these outer features here as Fermi-arcs. One can see that surface features also extend beyond the projected Weyl points, which you would not at least expect in an ideal model where these Fermi-arcs become bulk states once they reach the Weyl points. And in fact, in these early ARPES papers, first reporting electronic structure results on these compounds, the identification of what specific features of Fermi-arc has not been consistent. So there's still some open questions also regarding the surface electronic structure. So we studied this compound tantalum phosphide using synchrotron ARPES, and this is now data in the VOV regime where we are rather surface sensitive. This is a comparison between ARPES data along various high symmetry directions to DFT calculations. And if you take the time to compare all the different features, what you find out is that basically all the features that observed in the experimental data correspond to surface states. So really these experiments only probe surface states. We can now look in more detail at the predictions or at the potential Weyl physics here. So these are now Fermi surface maps for the same sample. And here on the right, you can see as a guide a DFT calculation where we have these projected Weyl points, basically at the separating the spoon-like outer features and this third feature here. So in the experimental data, we would expect them roughly here at these points. And now similarly as in the DFT calculation, also in the ARPES data, there's no real, or at least no clear signature that these are really arcs that completely lose their intensity at these projected Weyl points, but rather these states extend over the positions where we would expect the Weyl points. However, what is interesting when you look at the dichroic signal, so this is the linear dichroism, basically the left-right asymmetry obtained for when you're using depolarized light, what you see is that in both geometries, so along the kx direction and also along the ky direction, there are characteristic switches in this dichroism at the projected Weyl points. So this is marked by these arrows here. When we move here along this contour, at the point where the Weyl points in the bulk are located, the dichroism of the surface states suddenly switches. So there seems to be something definitely going on at these particular points in momentum space, and we can use DFT calculations to understand this in more detail. So what happens is that when you project your surface Fermi surface on particular orbitals, then you can actually also see this effect similarly as in the experiment. So when we project here on this on these types of orbitals, these features indeed look like Fermi-arcs. So they really vanish once they pass these Weyl points. And this other surface feature here has a completely different orbital character. So there's a sudden change in orbital character of these surface features once they pass this projected Weyl points. And this is the reason why we can have these signatures here in spectroscopy. The sudden change in orbital character changes the matrix elements and leads to these effects in the dichroic signal. And we also see similar effects in the Bayer intensity in this measurement here for S-polarized light, where, for example, these spoon features or these arcs are completely suppressed along one direction, and then the other feature here in the other direction is completely suppressed. So there are consistently spectroscopic signatures at the projected Weyl points. And we use DFT calculation to understand this behavior in more detail. So by looking at the localization in real space of these states, and what we find is that these states that we here call alphas, or these outer surface states, they are very localized in the very first atomic layers, while the states become increasingly bulk delocalized when approaching this W2 point and going beyond this W2 point. So this would be these wave functions here in the middle, which clearly extend more into the bulk than the surface states here. So and this is a possible explanation now that unlike in the ideal models where once the Fermi-arc reaches the Weyl points, you become fully delocalized in the bulk, get a pure bulk state. Rather, what we propose here is that these states become more delocalized, but still retain a sizable surface weight at least. So this would be something in surface science that would be called a surface resonance. And another confirmation for this interpretation is the fact that this feature beta here, which would be the surface resonance, has a very similar orbital character as the projected bulk Fermi surface. So when it can interpret this in a way that the Fermi arcs kind of adopt their orbital character to the one of the bulk states and hybridize with these bulk states to form surface resonances once they reach the projected Weyl points. Okay, now going towards probing the bulk states. So it has been shown already in these very nice early papers on these materials that one can use soft X-ray ARPES to address the bulk states. And now our idea was to go beyond just probing the dispersion of the bulk states and to also probe the spin and potentially other properties of these bulk states. So this is a sketch here of the experiment when increasing the photon energy going towards the so-called soft X-ray regime, the final states become more bulk localized and allow for a higher bulk sensitivity of the experiment. And this is already seen here in this data set taken at 590 eV, where now, completely different from the previous results, the spectra or the measured dispersion nicely matches the calculated bulk band dispersion. So there's no prominent sign, at least, of surface states. And in the calculations, we can see here that these states are indeed expected to be spin polarized. So this color code of the bands here corresponds to the spin polarization of these states. And so we took spin resolved data at certain points in momentum space, indicated here by these dashed lines. So these are the corresponding energy distribution curves with for spin up and spin down sensitivity. And one can see a certain shift between these two spectra, confirming that indeed these bands here are composed of two components with opposite spin polarization. And once we go from positive wave vectors to negative wave vectors, this spin polarization changes sign. So this is a demonstration that indeed also these bulk states are spin polarized, which is a prerequisite for the Weyl physics. What is a little bit a problem is that, at least with our setup, we are not able to achieve sufficient momentum resolution to really study the details of the spin polarization, for example, close to the Weyl points. So we were looking for another signal that is easier to obtain and still contains information about the character of the electronic states. And it turns out that the circular dichroism is again very useful here. So one interesting observation is that the inversion symmetry breaking not only induces the spin polarization of the electronic state, but it also gives rise to a finite orbital angular momentum of the states, which would not be possible in centrosymmetric systems. And one can see this here in the DFT calculation. So this is again a bulk band structure cut through through the bulk band structure projected on the orbital angular momentum, and one can see that there are sizable orbital angular momentum components which show certain k dependence. And this is now, for comparison, the same experimental cut here, where the color code is the circular dichroism, and one can see, in fact, a very nice correspondence between the calculated orbital angular momentum and the circular dichroism. And this is probably not a coincidence, because there have been theoretical predictions saying that once the final state of our photoelectrons is close or approximately free electron-like, then indeed the circular dichroism signal should be related to the orbital angular momentum, in particular the component projected on the propagation direction of the light, which is also what we compare here in this comparison. So we can also look at this over entire K-space. So this is essentially here covering now the full Brillouin zone. And what we did here was to integrate over the entire valence band here, the first valence band. So each point in momentum space here gives some contribution, and we can compare the dichroism, the measured dichroism, to the calculation of the orbital angular momentum, and indeed there's a nice correspondence between both. So now one question is whether the orbital angular momentum that we can apparently address spectroscopically here is related to the Weyl physics or to the Berry curvature. And at least under certain, in certain cases, there is indeed a relation between Berry curvature and the orbital angular momentum. So there's been a very nice theory paper recently suggesting that circular dichroism could be a probe in certain cases of the Berry curvature in momentum space, essentially based on this relation to orbital angular momentum. And this is what we looked at here now in more detail. Now we are zooming in a little bit on the region in momentum space where the Weyl points are located. So these are indicated here, and we are considering a constant energy cut at an energy slightly off these Weyl points. And we compare here the orbital angular momentum projection theoretically and the Berry curvature. And indeed the textures are compare quite well. So there seems to be some similarity at least. And also our circular dichroism seems to show these characteristic sign changes when moving along this contour. And one can theoretically go in even more detail and calculate the winding number of the orbital angular momentum across these Weyl points, and also of the Berry curvature. For the Berry curvature, it's obvious that the winding is topologically non-trivial, but it turns out that the orbital angular momentum winding is also topologically non-trivial. So both quantities have the same same winding number in this case, whereas theoretically it turns out that the spin is in fact topologically trivial in this compound here. So it's really the orbital degrees of freedom that that carry the topological information in this particular compound. So we believe that with these experimental data, we get at least some experimental signatures that really the Bloch states close to the Weyl points show this theoretically predicted non-trivial winding. Yeah. Okay, and with this, I'd like to summarize. So I believe we have a very interesting new platform here to study interplay between magnetism and topology with various experimental probes. And in particular, yeah, we are now trying to go towards compounds with higher N, and Anna has already very nicely introduced also these antimony-based compounds, which could be interesting. And then I've shown that dichroism in ARPES can yield signatures both of the surface and also of the bulk Weyl physics in tantalum arsenide. Thank you.
Okay, thank you very much for this nice talk. Are there any questions? Yes, please go ahead.
Yes, I have a question about the small gap that you observe in the BT terminated.
Oh, it's still there.
Yes, that's right. Yes. You interpreted this gap due to the hybridization of the surface state with the bulk state. Could it be also just the hybridization of the top surface state of the BT with the bottom surface state of the BT?
No, this is impossible in this case because because these are single crystals. So we do not expect like this thin film coupling.
Oh, okay. Okay, and by the way, in this type of complex structures, do you think you see the electronic band structure of the whole material, or just you know, the few layers on top? Let's say if you have a BT terminated sample, you may see just the top BT layer and not too much of the bulk structure. Well,
yeah, definitely.
What do you think you see? Yeah.
Yeah, I believe in particular, for example, this gap that we see there. So the suppression of spectral weight. This is kind of a signature of exactly this effect, because I believe, or well, I cannot really confirm it, but I believe that from all our data that there should be bulk states beyond, below this, or filling up this apparent gap, and it's just effect of the finite probing depth of the experiment that these states in the gap are not probed.
Okay.
It's also a bit yeah, it's a bit weird. It doesn't seem to be just a cross-section effect, because for all photon energies we see this. So
okay.
So it really seems to be an effect of the mean free path. And yes, so in general, of course, we are, I think, only probing the first layer. The first van der Waals layer, if at all.
All right, thank you very much.
Okay, another question. Did you see any effects from the anti-site disorder according to your ARPES data in manganese bismuth tellurium?
Not really, I would say. I wouldn't know really what to look for. So I think ARPES is not really the technique to address this. I would not be sure what to look for in the band structure. So that would be, one would have to start with very detailed theoretical modeling, how it affects the band structure, and then one could maybe look at it. What maybe is a little bit surprising is that one can obtain very, very sharp ARPES features, despite the fact that there's apparently a lot of disorder, at least of this anti-site character. Doesn't seem to be detrimental so much.
Okay. Another question is, can you further comment the connection between dichroism and Berry curvature?
Well, I think this is still work in progress. As I said, I think what is kind of established that under at least certain circumstances, The circular dichroism is related to the orbital angular momentum, which I think is quite convincingly just shown a posteriori, even by a comparison between these data sets. And also the fact that there is theory predicting that once you have a free electron final state, there should be some relation. And one thing I didn't mention is that at these high photon energies, we are 600 eV above the Fermi energy. And of course, at some point, one should approach the free electron limit. So it kind of makes sense. And then, of course, it's a question. So there's one more subtlety, actually, more of theoretical character. So what we found out in the study here is that what we probe here, or what we call orbital angular momentum, is basically really this atomic expectation value. So it's basically the wave function is the Bloch wave function is projected on spherical harmonics, and so it's more like an atomic orbital angular momentum. Whereas there's also an orbital angular momentum defined in Berry phase band structure theory. So these two are not identical. And so if that were the case, then there would really be a direct connection. I think at present, it's both theoretically and experimentally not yet clear under which conditions you have the further relation to the Berry curvature. I think this one still has to look at in very much detail for each system. And in this tantalum arsenide, there seems to be at least some correspondence. But it might be that it's lost in other systems.
Have you tried your measurements for different photon energies?
Sorry?
I mean, did you measure for different photon energies? Because we only saw data in the talk for, I think in the first part was 6 eV, and this one is,
yeah,
because different photon energies in circular dichroism change the sign.
Yeah, of course this can happen.
Yeah, but then it doesn't match the Berry curvature, right?
Sorry?
But then there will be like, it would not match the orbital angular momentum calculations, right?
Yeah, so there are of course subtleties. So we have not. So what of course we tune the photon energy here in this case to just go into the KZ plane. So it's not so trivial as for the surface states, because you really have to also consider the out of plane component, and then you are at a certain photon energy at the Weyl points, and then you would have to go to other photon energies, and it turned out that this is very tricky in this case. So I cannot show you, let's say, the same result at another Weyl point, but what we have obtained now is more systematically data at different KZ values, and there this correspondence between dichroism and orbital angular momentum is still there. But I cannot exclude that at certain photon energies, of course, you get other effects. And so, of course, there's no one-to-one correspondence like energy and momentum conservation as for the band structures.
Okay, thanks. In manganese bismuth telluride, is it possible to control the localization of surface state by surface deposition of alkali metals or gas molecules?
Yeah, this would be actually an interesting experiment, but we have not tried that.
Okay.
I guess so, but
are there more questions? Guess not. There is Carmen Gomez. I mean, apparently so. Okay, Carmen Gomez, please, can you unmute yourself?
Hi, Hendrik. Thank you for the talk. It was very nice. Very nice images, or ARPES images. I would like to ask you, these samples, after being drawn, do they have any capping to avoid oxidation while transferring the sample to the ARPES setup? Or how do you do? Do you have a suitcase, vacuum suitcase?
No, I mean, most of the results I've shown are on the single crystals. So what we do there is that we actually cleave them in the UHV setup of the ARPES experiment. We are also doing experiments on MBE samples where this is always, of course, an issue. Okay. But they were not shown here.
Okay.
But yeah.
Okay, thank you very much.
Are there more questions? If not, okay, let's thank Hendrik again and all the speakers of the session. And I think you can further ask more questions in these discussion rooms. Thank you.
Thank you.